Okay, I'm back. So this third worksheet on vectors, I'm supposed to continue working on pairs of lines, but I just thought I'd uh, work on these two problems um, to complement what you already have done. Here we go. Prove that two vectors A and this one should be B prove that the two vectors A and B are perpendicular. Okay, I want to solve them in a different color. Solution in a different color. So you start off by saying if A and B are perpendicular, that would mean that A dot B should give me 0. So let me actually find the dot product and see whether or not I get 0. A dot B should therefore be equal to 3i minus 7j plus 2k dot 5i plus j minus 4k. And you would remember, when you're dotting two vectors, you simply multiply the corresponding I, j, and k coefficients. So it's the coefficients of I, 3 times 5, plus coefficients of j, minus 7 times 1, plus the coefficients of k, 2 times minus 4. That looks like 15 minus 7 minus 8, which gives me 0. What's my conclusion? My conclusion is that A and B are perpendicular. Once the dot product is 0, the two vectors are definitely perpendicular. Okay, the second problem, it's a little more interesting. They said to us if the angle between two vectors v1 and v2 is such that cos theta is 4/21, v1 is given, v2 is given, find the possible values of lambda. Notice v2 is given in terms of lambda. Here is where you invoke the mathematical definition of the dot product, which is v1 dot v2 should be equal to the modulus of v1 times the modulus of v2 times cos theta, theta being the angle subtended by the two vectors. They actually gave us cos theta as 4/21, so we can substitute for that directly. And we can plug everything in and massage the entire expression. So let's go. V1, which is, if this thing would write, 6i plus 3j minus 2k, and I'm dotting that with minus 2i plus lambda j minus 4k. That has to be equal to the modulus of the first one, which is the square root. Get away. Ciao. Which is the square root of 6 squared plus 3 squared plus a minus 2 squared. I gotta go to the next line, times the square root of minus 2 squared plus lambda squared plus a negative 4 squared times cos theta itself being just 4/21. Okay, let's tidy this up. v1 dot v2, let's dot the left hand side. This would be 6 by minus 2, that looks like minus 12, 3 lambda plus 3 lambda, and minus 2 by minus 4, that's plus 8. Gotta make sure my algebra is on point here. Algebra and arithmetic. That's the square root of 36 45, 49. That's not too bad. Times the square root of 16, and 4 is 20 plus lambda squared. Lambda squared plus 20. Times cos theta, which is 4 upon 21. On the left hand side, it looks like I have 3 lambda. Minus 4 is equal to, okay, the square root of 49 is 7. 7 will go into this 21 to give me 3. So the numbers on the outside will give me 4/3 times the square root of lambda squared plus 20. I'll do probably maybe one more step. Multiply throughout by 3, you get 9 lambda squared minus 12 is equal to 4 times the square root of lambda squared plus 20. And obviously I have to square both sides to get rid of that square root. So 9 lambda squared minus 12 all squared is equal to square root of 4, you get 16 into lambda squared plus 20. I think this is what I'm going to continuously do with quite a few problems. Instead of solving it all the way to the end, leaving it at a certain point where I know you should be able to take it from there. And you clearly will end up with a standard quadratic when you open up all your brackets and whatnot. And you should find two values of lambda. Yes, I'll leave that problem there. You finish it up. Lambda equal whatever, lambda equal whatever else. Okay, now I want to get back to line pairs. Let's talk about pairs of lines again. We said that there are 3 scenarios when you have pairs of lines in 3 dimensions. You can have a pair of lines that's parallel and they would never intersect, and it's very easy to prove that they're parallel. The vector equation of a line is written in the form r equal a plus lambda b, where b is the direction vector for the line. If you take the direction vector for each line, and you can write one direction vector as a scalar multiple of the other direction vector, it means that the two direction vectors are parallel, and therefore the 2 lines are parallel. So that's the first scenario. I dealt with that in a previous worksheet. The next scenario is where the lines are non-parallel and intersecting. They're not parallel to each other and they intersect. Let's take a look at that right now. Let's look at an example of that. The third scenario, of course, would be that they're non-parallel and non-intersecting. Okay. I can never find what I'm looking for. Just give me a minute. Jeez, man. Okay. Here I have a pair of lines. Prove that the pair of lines R1 is equal to I minus j plus 3k plus lambda into I minus j plus k and R2 is equal to 2i plus 4j plus 6k 6 Ugh. plus mu into 2i plus j plus 3k. Prove that these lines intersect. That's part A. Part B. Find the common point of find the position vector of the common point of intersection and part C. Find the acute angle between the lines. Okay. Now what we're going to start by doing is that for each line we're going to group the ij and k coefficients. So what we're going to do, we're going to expand out for line 1, multiply the lambda inside the brackets, and at the same time factor out the I from the two terms that have I. Same thing for the j's, same thing for the k's. So R1, Lord. R1 can now be rewritten as 1 plus lambda all times I plus a minus 1 minus lambda all times j plus 3 plus lambda all times k. Right? All I did was to multiply the lambda into the brackets. So you would have had I plus lambda I and factor out the I. Same things for the j, same thing for the k's. We're going to repeat for the second line. R2 is equal to 2 plus 2 mu all times I plus 4 plus mu all times j plus 6 plus 3 mu all times k. If the lines intersect, there must be a common point satisfying both lines. That is, there must be a common point such that R1 is equal to R2. So we'll put R1 equal to R2. That would mean that 1 plus lambda all times I plus minus 1 minus lambda times j plus 3 plus lambda all times k must be equal to 2 plus 2 mu all times I plus 4 plus mu all times j plus 6 plus 3 mu plus 6 plus 3 mu all times k. Okay, squeezing it in the corner there. Now, if we put two vectors equal to each other, and each vector is written in Cartesian notation, then clearly we can equate the ij and the k coefficients. So that's exactly what we'll do. Equating the coefficients of I, j, and k, we end up with three equations. One equation says 1 plus lambda is equal to 2 plus 2 mu. Second equation says minus 1 minus lambda is equal to 4 plus mu. And the third equation says 3 plus lambda is equal to 6 plus 3 mu. Okay, so I have three equations, but if you look at them, I only have two unknowns that I'm solving for. I don't need three equations to solve for two unknowns. At the maximum, I need two equations to solve for two unknowns. So I'll take two equations, and it could be any two of the equations. I'm going to choose to take the first two. Just give me a second here. I'm double checking something. 6 plus 3 mu. 3 plus lambda. Good. Yes. Okay. I'm going to choose to take the first two and solve for mu and lambda. So, if you think about it, if you add equations 1 and 2, just add these two, we'll get 1 plus a negative 1 gives me 0. Lambda plus minus lambda is 0. And that must be equal to 2 plus 4, that is 6. And 2 mu plus mu is 3 mu. From which I could get mu equal negative 2. Now that I have the value of mu, I plug it back into either one, let's say the first equation, and I got the corresponding value for lambda. So that will be 1 plus lambda is equal to 2 plus 2 times the value of mu, which is minus 2. That's minus 4 plus 2, that's minus 2. Looks like lambda is equal to minus 3. Lambda is equal to minus 3. Now, here is the important part of this proof. You just solved two equations for two unknowns. You have a third equation, an unused equation left over. In this case, it just happens to be equation 3. But I could have solved any two of the equations. I could have solved 2 and 3. And the unused one would have been equation 1. At this point, you take the unused equation, which happens to be equation 3 in this case, and you plug in both the value of mu and lambda. If the two sides of the equations balance, then the lines intersect. If the two sides of the equation do not balance, then the lines do not intersect. Very simple. So let's check it out. In equation 3, I'll write it back. 3 plus lambda is equal to 6 plus 3 mu. And I have a particular way I like to show that two sides are equal, even though this is something quite straightforward. I take each side separately and I prove what the value is when you plug in either lambda or mu. So for example, take the left-hand side, which is 3 plus lambda, and with lambda equal minus 3, you'll get the left-hand side giving you a value 3 plus minus 3, which is 0. Take the right-hand side, which is 6 plus 3 mu, and with mu being equal to minus 2, you will end up with 6 plus 3 times minus 2, which happens to be 0 again. Two sides are equal. By the way, they don't have to be equal at 0. They could be equal at some other value. So this particular example just happens to have them being equal at 0, but they could have been, two sides could have been 2 and 2, or 5 and 5, or 7 and minus 7. As long as the two sides are equal, that's what you're looking for. It means that the two lines intersect. So this implies that the lines intersect. So that's the proof for part 1. Part 2, or part A. Part B, find the position vector of the common point of intersection. Well, if you know that they intersect, then there must be a common point of intersection. How do you get that common point of intersection? You either take equation 1 and you plug in lambda, or you take equation 2 and you plug in mu. One or the other. In this example, I'm going to do both just to show you'll end up with the same thing. But, you know, obviously in an exam situation, unless you have time left over for yourself, you want to just plug it into one of them. So let's see. And by the way, I'm going to plug it into the form where I had already grouped the i's, j's, and k's. Makes your life a little easier. So lambda was minus 3. I'm going to plug into R1, which was 1 plus lambda all times I, plus minus 1 minus lambda all times j, plus 3 plus lambda all times k. And if I plug the value lambda equal minus 3 into that equation, I'll get R1 is equal to 1 minus 3 times I, plus a minus 1 minus into minus 3 times j, plus 3 minus 3 times k. R1 is therefore minus 2i, and that's 3 minus plus 2j, I think. Minus 2i plus 2j, yes. And of course, the k, 3 minus 3, it would give me 0. This represents the position vector of the common point of intersection. Or I could have plugged in mu equal minus 2. Mu is minus 2, I think, yes. Into equation 2. Let's see, what would that have been? 2 plus 2 mu R2 was 2 plus 2 mu all times I plus something 4 plus mu all times j plus 6 plus 3 mu all times k. And let's see, with mu equal minus 2, I will get R2 is equal to 2 plus 2 times minus 2 all times I, plus 4 minus 2 all times j, plus 6 plus 3 times minus 2 all times k. Let's see what happens here. R2 is equal to, this looks like a minus 4 there, plus 2, which is minus 2i. 4 minus 2 is plus 2j. 3 by minus 2 is minus 6, plus 6 is 0. So, voila. Got the same thing. You don't need to do both, but in a studying environment, it's not a bad idea to confirm or prove to yourself that either one would have worked. And so we just proved that they intersected. All you need to show is that the three equations, the unused equation out of the three that you got when you equated the coefficients, the unused equation, the two sides will balance when you plug in the value of mu and lambda. That will prove that the lines intersect. If you want to find a common point of intersection, you plug in either mu into the first one, lambda into the first one, or mu into the second one. The third part, interesting enough, is asking for, let me make sure I blah, blah, blah. Find the acute angle between the lines. Okay. Well, let me see if I can represent this. Here, let's assume that these are the two lines. Okay, this is the line L1 with equation R1. And this is the line L2 with equation R2. Now remember, parallel to each line, you will have the direction vector for that line. Let's call this one B1. And parallel to this line, you're going to have the direction vector for that line, B2. You can clearly see from what I'm trying to represent here that the angle between the two lines would be the same as the angle between those two direction vectors, theta. Now, which therefore means if you can find the angle between the two vectors, the two direction vectors, that would represent the angle between the two lines. Now, it is possible that when you find that angle between the two vectors, it ends up to be obtuse. All that would mean is that the other vector, the B2, for example, was actually pointing this way. Let me change my color, make this thing interesting. All that would mean is that B2 was pointing this way instead. This was B2. And you ended up finding this angle. Well, normally when you specify the angle between two lines, you want to specify the acute angle between the lines. So when the angle, if your calculations show that the angle is obtuse, you simply subtract it from 180 to get the acute angle between the lines. Right? All right. So let's proceed. We write a nice little statement here which should solidify what I'm trying to say. That is, the angle between two lines is the same as the angle between the direction vectors parallel to the lines. So let's go back to those two lines. In the first vector equation, the direction vector B1 was I minus j plus k. And B2, here's B2, was 2i plus j plus 3k. So if you want to find the angle between those two vectors, you simply find the dot product. Invoke the dot product expression and you're good to go. So let's try that. B1 dot B2 is equal to the modulus of B1 times the modulus of B2 times cos theta, where theta is the angle between the two vectors, and hopefully if it's acute, then that also represents the acute angle between the lines. If it's not acute, then 180 minus that angle would represent the acute angle between the lines. So let's dot I minus j yes, I minus j plus k dot 2i plus j plus 3k must be equal to the modulus of the first one, the square root of 1 squared plus or minus 1 squared plus 1 squared times the root of 2 squared plus 1 squared plus 3 squared cos theta. 1 minus 1, 1, 2, 1, 3. Okay. Okay, if I dot on the left hand side there, I'll get 2 times 1 plus minus 1 times 1 plus 1 times 3. That's root 3, it looks like, times root, and it looks like root 14, I think. 9, 10, 4, 14, cos theta. Okay. This is 2 and 3 is 5 minus 1 is 4. 4 divided by the square root of 14 by 3 is 42. You can put both under the same square root. Square root distributes over multiplication. I think 14 threes is 42. Yes. And that's equal to cos theta, from which we can say theta is equal to cos inverse of whatever that is, 4 over the root of 42. Until I can fire up one of these calculators and find this. I'm a real klutz in using this stuff. Man, y'all sending me back to school here. Yeah. I don't know. .7 degrees, I think. All right, so that's the angle. That's what I got. Y'all gonna double check me, because yeah, you can double check it. That's the angle between the two vectors, and therefore that should be the angle. That's the acute angle between the two lines. Right. There's one more thing I want to do in this tutorial. No, I gotta do 2 more things. I gotta check a line pair. Ooh, let's keep going. Yes, the third scenario where the lines are non-parallel and non-intersecting. Ooh. Yes, that's possible. These are called skew lines, skew lines. Let's find a pair. I'm going to leave most of the work here for you guys. In fact, I'll write these vectors in, let's do this one in column vector notation. First line R1 is equal to 1, 0, 1 plus lambda into 1, 3, 4. And R2 is 230 plus mu into 4 minus 1, 1. Okay, and the question is, basically, prove that these lines are non-parallel and non-intersecting. Prove that they're skew lines. So what we'll do is what we did before. Group the i's, j's, and k's from each equation. So from R1, I should get a column vector that looks like this. 1 plus lambda, 3 lambda, and 1 plus 4 lambda. And from R2, I should get an expression that looks like 2 plus 4 mu, 3 minus mu, and mu. Now we're gonna repeat that same statement before. If the lines intersect, we're gonna end up with a kind of a contradiction here. But that's how we're gonna start out with the making the assumption that if they intersect, then there must be a common point such that R1 is equal to R2. So we're going to put R1 equal R2, which would imply that 1 plus lambda, 3 lambda, and 1 plus 4 lambda is equal to 2 plus 4 mu, 3 minus mu, and mu. And of course, if we equate the I, J, and K components, we get 3 equations again. The 3 equations are 1 plus lambda equal 2 plus 4 mu. Second equation says 3 lambda is equal to 3 minus mu. And the third equation says 1 plus 4 lambda is equal to mu. Equation 1, equation 2, equation 3. If we solve the first two, you don't have to always solve the first two. There's no reason for me wanting to even trying to solve the first two. In fact, let me see. I will solve the second and the third. It looks like a nicer prospect, and I will add them. If you add the two equations 2 and 3, you get 1 plus nothing is 1 plus 3 lambda plus 4 lambda is 7 lambda is equal to 3 plus nothing is 3, and minus mu plus mu is 0. If we add 7 lambda is equal to 4, which means that lambda is equal to 4/7. If I take the value of lambda and plug it into the third equation, I will get mu is equal to 1 plus 4 lambda, which is 1 plus 4 times 4/7. Mu is equal to what? 16/7 plus 7/7. 23/7. Mu is 23/7. And lambda is 4/7. What we're going to do now, we're going to take those two values and plug it into the unused equation. In this example, the unused equation happens to be equation number 1. So let's plug in. On the left-hand side of equation 1, we have 1 plus lambda, which is 1 plus 4/7, which is 11/7. On the right hand side, we have 2 plus 4 mu, which is 2 plus 4 times 23/7. And I don't even need to calculate that to see that the two are not the same. I'll try to calculate it anyway. 2 is 14/7 plus, Lord have mercy, 4 3 is 12, 4 2 is 8, and 192, I think, over 7. 92, 100, 206, 106 over 7. The left hand side and the right hand side are not equal. Which implies that the lines do not intersect. By the way, there's something very important I forgot to do at the very beginning. What I should have done was to check to see if they were parallel. That's always the first thing you should do. I messed up, so I'm correcting it now. Because clearly, suppose they were indeed parallel, then after all this calculation, we'll still show that they didn't intersect, but that doesn't mean that they're skewed. Compare the two direction vectors. Let me go back right up here. Squeeze a little space out here somewhere. There. The two direction vectors, B1 is 1, 3, 4, and B2 is 4 minus 1, 1. And there's nothing you can do with the first direction vector to get the second one. Here's what. Suppose I wanted to see what the scalar multiple is, if they were indeed parallel. Take B1 and multiply the I coefficient by 4. And multiply B1 by 4, sorry. If you multiply B1 by 4, the I coefficient will match the I coefficient for B2. But immediately, the 4 by the 3 will give you 12 for the J coefficient for B1. And the J coefficient for B2 is minus 1. So clearly, they're not parallel. Not parallel. And I probably should have gone up to, which one? This one. All the way up here. And done the same thing. B1 for this one is I minus J plus K. And B2 is 2I plus J plus 3K. And take B1, take the I coefficient, take B1, start multiplying it by 2. 2 by I will give me 2I. Yes, that matches the I coefficient for B2. But the same 2 by the minus 1 in front of the J will give you minus 2. And that doesn't match what's in front of J in B2. So therefore, they're not parallel as well. You should always check for that first. All right, so that's corrected. This is a rather lengthy video, so I'll stop here and I'll continue. I'll start another video with some other stuff. You have to know what's called the parametric equations and the Cartesian equations for a line. I'm going to do that in another video though. I also have to do the vector equation and the Cartesian equation for a plane. So I want to finish this up, and then that would finish up your vector analysis in total. So 1, maybe 2 videos, depending upon how long each one takes. All right, I'm out.